this. Again, make sure that we're all on time to the lab because I have to repeat things twice if you get here late, and also just make sure you follow the instructions quite closely so that we don't end up in this position in the future. All right, so on your lab reports, make sure you have your name, student number, group members' names, as well as your section. That, I believe, is the wrong section. It's L2, correct?
L5.
L5? Yeah. Okay, so you get 5% for that. Okay, now for summary. This summary is going to be a little bit different than probably what you guys are used to. I want you guys to write it similar to a paper abstract. So a summary for this course will have an objective as well as a major results section. Just a couple lines. I'm literally going to tell you what they are, but the objectives for this lab are to examine grain structure.
We can just write what you're saying?
Yeah. Identify major constituents. Identify major constituents, so phases. And become familiar with metallographic preparation techniques.
Become familiar with what?
Metallographic preparation techniques.
What's a graphic?
Metallographic, so that's like metallography.
Oh.
That's what this course is about.
Metallographic examine.
Preparation techniques. Okay. Summarization of major results and conclusions. There are 3 major results I want you guys to mention. I want you to mention the identity of the unknown sample, which I will explain how you guys are going to determine. I want you guys to mention the grain size estimate for the iron ingot sample, which I'm going to explain to you guys. And I want you guys to mention the trend in etch response time.
Wait.
We'll send you.
All right, I'm going to repeat that. Identity of unknown. Grain size estimate. Etch times.
Do we have to graph that relationship? Or?
Nope, just mention briefly the 2 etch times. Etch times.
Do you want this typed up?
You can type it up, you're welcome to type it up. If you have neat handwriting, you can write it into the template. Alright, you get 15% for having a perfect summary. In the summary, please remember, you do not use references such as references to figures, tables, or the like from the body or report, and I don't want any cited sources. This is because this is a standalone document. You should be able to pick it up, read it, and understand everything to do with the report. You shouldn't have to follow any references used in the summary because there shouldn't be any. Does that make sense? So I don't want you to say turn to page whatever to find out what the identity of the unknown sample is. I want you to say the identity of the unknown sample is BAM. Make sense? Okay. Now, moving on to the results section, you need to complete etch times for your 2 metals that you prepared. So that's your iron ingot and your unknown. The other 2 boxes, just draw a line through them. For your micrographs, that's your pictures. You need to identify what the sample is. You need to identify what the magnification you used is. And the magnification should be 500 times. That's because the lens is 50 and the microscope is 10. 50 times 10 is 500. Make sense?
Yeah.
In each box. You need to say it on each box.
Multiply the
What?
lenses.
The actual microscope is 10 and the lens is 50. So that's 500 total. So I need you to write 500 times magnification for each and every sample picture.
Under additional observation?
Yes. I also want you to identify the phases that you see and draw an arrow pointing to which phase is which. So that's your pearlite and your ferrite. Pearlite's black, ferrite's white, or lighter color. I also want you to outline a grain for the iron ingot sample. Take a Sharpie or whatever and outline a grain so that I know that you guys understand what a grain looks like. Okay? For the iron ingot sample calculation.
Would you say that
Sorry.
perlite is black? Sorry. And then
Perlite is black and ferrite is white.
ferrite is white.
So we need to sort of define that? Or
Yeah, so write perlite and draw an arrow to where you see perlite, and write ferrite and draw an arrow to where you see ferrite.
One example or all of them?
For each and every one, you need to identify what
Like the one
phases you see.
picture, do I show all the black?
No,
ones
no,
or
no, no, just once for each picture. Some samples don't have perlite, other samples do. And the iron ingot does not have perlite. Okay, so the ingot iron grain size calculation, you're going to use this calculation here. I want you to label your variables, I want to see the equation, and I also want to see a calculation for the average number of intersections. So I want to see that you've taken 3 measurements, divided by 3, and that you have an average number and that you're using in this, okay? On top of that, I want to see how you're going to calculate your magnification factor. The way that you calculate your magnification factor is by dividing what a measurement would be on a screen versus what it is in real life. It says it on the table over there, but I'm just going to give it to you guys, okay? Because the magnification in the lens is not the same as the magnification on the screen, and et cetera, et cetera. So, it's going to be 200 millimeters.
Wait, what's 200
That's the measurement on the screen,
Magnification?
is equal to 0.1 millimeters in real life. So if you divide the two, you get the multiplication factor for the screen to real life.
for 200 millimeters is 0.001?
Yeah, if you write, I'm giving everything in millimeters, so the millimeters will all cancel out, so it doesn't matter. So 200 millimeters divided by 0.1 millimeters.
0.1.
Millimeters. What does that equal? Anybody?
2000.
2,000 times. So your magnification factor will come out to be 2,000 times. Give me the calculation so that I understand that you understand how you got that 2,000 number. Does anybody-
Divided by 0.1
200 millimeters divided by 0.1 millimeters. M equals boom.
What was the 500 times magnification?
That was the magnification of the lens, but plus the microscope. There's an electronic magnification between the actual microscope and the screen. Does that make sense?
Screen in real life.
Right.
Yeah, so I'm going screen to real life.
Okay.
That's what I'm doing.
What was that 500 times magnification?
That's the magnification, the actual microscope itself. So, okay, I'll explain it. There's 2 lenses, and then there's a camera. The 2 lenses have a magnification of 500. The camera has a different magnification when it sends it to the screen, so it alters the geometry of the picture. So there's a different magnification versus the optical versus the electronic magnification. Make sense?
Yeah.
You guys don't have to understand the whole thing, but just understand that the magnification factor is 2,000. You calculate it by dividing 200 by 0.1. We clear?
Yeah.
All right. Sorry, I'm going through this so fast. It's because there's another lab right after this, and we're gonna get thrown out. And I want to make sure that you guys have everything you need. Okay. So average grain size calculation, average intersections calculation. So whatever you got, like 4 plus 5 plus 4 divided by 3 or whatever. And then also your magnification factor calculation, okay? We good? Anybody want me to repeat something?
Just for like L divided by N, is that a comma or
L divided by N1, or I. It's a subscript, sorry. Yeah, my handwriting is really messy. Also, for monitor length, you want your grain size to be in millimeters or micrometers. So make sure that your L is in proper units.
The for the man, I forgot. Oh, for the summary, you said don't imply the other stuff.
Yeah.
Can we not write just what you told us?
Yeah, you can write exactly what I told us.
Okay.
Told you, just don't reference the body
Okay.
of the report. Don't be like, turn to page whatever to find this, or
Yeah.
as is stated in table 1. Don't do that.
Okay.
Okay.
So the only variations between the grain size calculations are the intersections?
Yeah, so you're only doing 1 because this is an average grain size calculation.
Well, they said the 3 values divided by.
Yeah, so you take the 3 values divided by 3,
Oh,
and then that gives you your average number of intersections. Make sense? All right. Sorry I'm going so quickly again. It also doesn't help that I've got a really bad cold. Okay, so next I need you to give me the identity unknown sample. I'm going to give you as a hint. There were only 2 types of steels used for this lab. And you've gotten 2 samples that I've already given you. So that would suggest that the unknown sample would probably be a sample you've already seen in this lab.
Wait, don't we have 3 samples?
But the iron's not a steel. It's an iron.
Okay.
Does that make sense?
Okay. So
It's pretty straightforward for you guys.
So we just pick the one that resembles the other 2.
Based on your engineering judgment, given the pictures as well as the etch time, understanding the etch time is related to carbon
We
content.
don't have the etch times for the samples for this.
I'm
Yeah.
talking about in comparison to your iron, so it's
Okay.
carbon content linked.
I see.
So, you have your unknown identity, but you also have to justify it. So when you justify what the identity of the unknown is, I want you to reference the picture that you're taking and how the carbon content looks similar to such and such picture taken from this, because you know that there's more or less perlite, which is more or less distributed within the ferrite depending on your carbon content. Does that make sense? So give me a reason why you chose one sample over the other. Give me a little explanation. I want you to mention carbon content.
Do we put that in our summary or in
No, do not put that in the summary. Put that in your additional observations where you identify your unknown sample. There should be a line that says what is the unknown sample. So on page 3, it's what is the unknown sample. You write the unknown sample, and in your additional observations you explain why you identified that. Make sure that in that additional observations you also have your magnification and you've drawn arrows identifying the faces that you see in that sample. Are we clear?
Yeah.
All right. So moving on to discussion questions. Discussion question number 1, discuss the effect of increasing carbon content on the amount of perlite and cementite, Fe3C, in the microstructure of plain carbon steel. So I'm going to give you a couple of words about this just to, I guess, lead you guys down the right track. So you've got 2 types of things in your microstructure of a hypoeutectoid steel. Hypoeutectoid means that the carbon content is below 0.8%, okay? In those, the 2 phases that you will see are ferrite and perlite. Now, perlite's kind of funny because it's actually a combination of 2 different phases. So perlite is called perlite because it looks actually like what would happen if you were to cut a pearl in half. A pearl that's been cut in half has a lamellar structure, which you guys may have heard of in class potentially. So that means it's layered, okay? That layering comes from a layering of it's ferrite, which is just pure iron, and cementite, which is Fe3C, okay? So you've got a layer of cementite and then perlite, cementite, perlite, cementite, perlite. Because the cementite is black, it comes out as the stronger color, which is why perlite looks black. If you zoom in close enough, you will see the lamellar structure. Make sense? So, as you increase your carbon content in a steel, you increase your Fe3C, right? The Fe3C consumes the ferrite, which is just the pure iron, to create Fe3C, your cementite. The cementite then layers itself with the ferrite, which also consumes ferrite, to increase your perlite content. So, in general, you'll increase your perlite content as you increase your cementite content, and you will decrease your ferrite content as carbon content increases. Does that make sense? Everybody understands what's going on there?
So perlite is cementite?
No, perlite is a combination of ferrite and cementite.
Too big.
All right, so discuss the effect of grain size on the strength and toughness of metal and explain why. So, in this you need to discuss grain boundary area, Write this down. This is really important. So grain boundary area. You also should write down resistance to dislocation motion. That's a buzzword in material science. So resistance to dislocation motion. Pardon me? Resistance to dislocation motion. If you don't know what that is, strongly recommend you look it up in your textbook. Really, really important term that will be used constantly throughout this course. And I also want you to explain to me how an increase or decrease in grain size will affect your DBTT and how indirectly that will, or well, directly that will affect your toughness. So DBTT stands for ductile to brittle transition temperature. And depending on your grain size, as your grain size increases or decreases, that will increase or decrease your ductile to brittle transition temperature, and that transition temperature dictates your toughness for a metal. DBTT. So just kind of talking here, you don't have to record what I'm saying, but basically, as your grain size changes, your DBTT will go up or down. As it goes up or down, that determines the point where your sample goes from a ductile sample to a brittle sample. Ductility and brittleness are directly related to your toughness, okay? So as that goes up or down, your toughness will go up or down, right? So if grain size is related to your DBTT and your DBTT is related to your toughness, that's the connection there. And then grain size is also directly related to strength based on the dislocation motion. Does that make sense? All right. So, last question. Compare the etch response times in the iron and unknown samples. Is this expected? Why or why not? So you need to talk about preferential corrosion. And carbon content. As well as areas of high stress
Areas of high stress.
and interstitial atoms. Interstitial. Another buzzword in material science. It basically means something that's jammed in between things.
So for like a size of these answers, are you like
Like a paragraph. I'm basically giving you the words that you need to basically piece together like 3 sentences to explain. Okay? Interstitial atoms. So, basically what's going on with the carbon content is acid attacks carbon faster. It also attacks areas of high stress faster, which means your grain boundaries. So something that has more grain boundaries and has higher carbon content will have a faster edge time because the acid attacks these more readily. Make sense? Okay. There is a literature review on the board here that basically explains the chapters which are relevant to the lab report. It's worth reading if you get stuck on something, you don't know how to explain something, okay? My email is also up there, Andrew Fawcett, top one.